and the overarching expansion of the universe. While the vast distances between galaxies might suggest isolation, their gravitational interactions often lead to collisions, particularly within dense clusters. Contrary to what one might imagine, galactic collisions are not violent events in the traditional sense. Individual stars within galaxies are so far apart that direct collisions between stars are exceedingly rare. Instead, the interaction primarily involves the gravitational forces of the galaxies, which distort their shapes, redistribute gas and dust, and trigger intense star formation. These interactions can also lead to the merging of the galaxies into a single, larger entity. The process of a galactic collision begins when two galaxies come within each other's gravitational influence. As they draw closer, their mutual gravitational forces distort their structures, stretching them into elongated shapes called tidal tails. These tails are streams of stars and gas that are flung outward, often creating stunning visual patterns. The Milky Way and the Andromeda Galaxy, for instance, are expected to produce such features when they collide in about 4.5 billion years. During the collision, gas clouds within the galaxies compress and collapse, igniting bursts of star formation. This phenomenon, known as a starburst, can lead to the creation of millions of new stars within a relatively short period. Some of these stars are massive and burn brightly, eventually ending their lives as supernovae, enriching the surrounding interstellar medium with heavy elements. The newly formed stars and their remnants contribute to the evolution of the galactic structure, adding complexity to the resulting system. Galactic collisions also play a critical role in the growth of supermassive black holes, which reside at the centers of most galaxies. As galaxies merge, their central black holes are drawn together, eventually forming a single, larger black hole. During this process, the inflow of gas and dust toward the black holes can create active galactic nuclei, among the brightest objects in the universe. These luminous centers emit intense radiation as matter is accreted onto the black hole, providing a unique opportunity for astronomers to study these enigmatic objects. One of the most famous examples of a galactic collision is the Antennae Galaxies, located about 45 million light-years away in the constellation Corvus. This system, formed by the collision of two spiral galaxies, showcases dramatic tidal tails and regions of intense star formation. Observing such systems provides valuable insights into the dynamics of galactic interactions and the processes that shape the universe. The outcomes of galactic collisions depend on several factors, including the masses, relative velocities, and angles of approach of the colliding galaxies. In some cases, the galaxies merge to form a single, more massive galaxy, often an elliptical one. In others, the galaxies may pass through each other, separating but leaving behind significant structural changes. In rare instances, the collision can lead to the complete disruption of one or both galaxies, scattering their stars and gas into the surrounding space. As our understanding of the universe has deepened, so too has our ability to simulate galactic collisions. Advances in computational power have enabled astronomers to create detailed models of these events, allowing them to explore scenarios and predict outcomes. These simulations not only reproduce the observed features of galactic collisions but also provide a window into the future of our own galaxy. The impending collision between the Milky Way and the Andromeda Galaxy, known as M31, is a subject of great interest to astronomers and the public alike. Currently separated by about 2.5 million light-years, the two galaxies are on a collision course, moving toward each other at a speed of approximately 110 kilometers per second. Despite the vast timescale of the event, simulations have revealed a detailed picture of what is likely to occur. The collision will begin with the outer halos of the galaxies interacting, followed by the merging of their disks and central regions. Over billions of years, the galaxies will settle into a single elliptical galaxy, likely surrounded by a halo of scattered stars. While the idea of a galactic collision might seem apocalyptic, it is essential to remember that these events are natural processes that have been occurring since the universe's earliest days. They play a fundamental role in shaping galaxies and driving cosmic evolution. The redistribution of gas and dust, the formation of new stars, and the growth of supermassive black holes are all critical processes influenced by these interactions. Galactic collisions are also a testament to the power of gravity as the dominant force shaping large-scale structures in the universe. Despite the immense distances and timescales involved, the outcomes of these collisions are governed by the same physical laws that dictate the motion of objects on Earth. This universality of physical laws underscores the interconnectedness of all phenomena in the cosmos, from the smallest particles to the largest galactic structures. Understanding galactic collisions not only enriches our knowledge of the universe but also provides context for our place within it. The Milky Way's eventual collision with Andromeda is a reminder that even seemingly static structures like galaxies are dynamic and ever-changing. By studying these events, we gain a deeper appreciation for the complexity and beauty of the cosmos. Galactic collisions are not isolated events but part of a broader tapestry of cosmic evolution. The universe, in its infancy, was a hot, dense state dominated by a nearly uniform distribution of matter and energy. Over time, tiny quantum fluctuations in this early state were amplified by gravity, leading to the formation of the first structures. Small proto-galaxies began to form, merging and interacting to create larger and more complex systems. This hierarchical process of galaxy formation and evolution is driven by the interplay of gravity, dark matter, and baryonic matter. Dark matter, an invisible and enigmatic form of matter that makes up about 85% of the total mass in the universe, plays a crucial role in galactic collisions. Galaxies are embedded in massive halos of dark matter, which extend far beyond the visible components of the galaxies. During a collision, these halos interact gravitationally, influencing the dynamics of the event. Dark matter also acts as a scaffolding for the formation and evolution of galaxies, dictating their large-scale distribution and clustering in the universe. One of the most striking aspects of galactic collisions is their role in driving starburst activity. The compression of gas clouds during a collision triggers the formation of massive clusters of stars. These starburst regions are often visible as bright, blue patches in the optical spectrum, signaling the presence of young, hot stars. In addition to optical observations, these regions can be studied in other wavelengths, such as infrared and radio, which reveal the intricate details of the gas and dust dynamics. However, not all gas in colliding galaxies is consumed in star formation. Some of it is expelled into the intergalactic medium through powerful winds driven by supernova explosions and the activity of supermassive black holes. This process, known as feedback, plays a critical role in regulating star formation and enriching the intergalactic medium with heavy elements. These metals, forged in the cores of stars and ejected into space during their deaths, are the building blocks of planets, life, and everything we see around us. Another fascinating outcome of galactic collisions is the formation of peculiar and irregular galaxies. These systems often exhibit unusual shapes, such as rings, bridges, and tails, which are the result of gravitational interactions. For instance, ring galaxies, like the iconic Cartwheel galaxy, are thought to form when a smaller galaxy passes through the center of a larger one, creating ripples of star formation that propagate outward like waves on a pond. Similarly, tidal bridges and streams are formed as material is pulled from the colliding galaxies, connecting them in a delicate cosmic dance. The study of galactic collisions has been revolutionized by advancements in observational technology. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have provided unprecedented views of colliding galaxies, revealing their intricate structures and the processes at play. Ground-based observatories equipped with adaptive optics and radio telescopes have also contributed significantly, enabling astronomers to study these events across a wide range of wavelengths. These observations, combined with theoretical models and simulations, have deepened our understanding of the physics of galactic interactions. One of the most intriguing aspects of galactic collisions is their potential to create new environments for the emergence of life. The redistribution of gas and the formation of new stars can lead to the creation of planetary systems in regions where conditions are conducive to life. While the direct effects of a collision on existing planetary systems are uncertain, it is conceivable that the gravitational perturbations and influx of material could spur the development of habitable environments. This possibility adds a profound dimension to our study of galactic collisions, linking them to the broader question of our cosmic origins. In addition to their scientific significance, galactic collisions have captured the imagination of artists, writers, and the public. These events, with their dramatic visual impact and immense scale, serve as a reminder of the grandeur and dynamism of the universe. They challenge our perception of time and space, inviting us to contemplate the vastness of the cosmos and our place within it. The study of galactic collisions is not only a pursuit of knowledge but also an exploration of the beauty and complexity of the natural world. The Milky Way's eventual collision with the Andromeda Galaxy offers a unique opportunity to observe such an event up close. Although this collision is billions of years away, its effects are already being studied through detailed simulations and comparisons with observed systems. These studies suggest that the resulting galaxy will likely be a large elliptical galaxy, potentially surrounded by a system of satellite galaxies. The fate of the solar system in this scenario is uncertain, but it is unlikely to be directly affected, as the vast distances between stars make direct collisions exceedingly rare. Beyond individual collisions, the study of galactic interactions provides insights into the large-scale structure of the universe. The distribution of galaxies in clusters and superclusters is shaped by their interactions, including mergers and accretions. Observing these structures allows astronomers to test theories of cosmology and the role of dark matter and dark energy in shaping the universe. Galactic collisions are thus not only events of local significance but also key to understanding the evolution of the cosmos as a whole. Galactic collisions also serve as cosmic laboratories for testing the laws of physics on massive scales. These interactions provide insights into fundamental forces, including gravity and hydrodynamics, under extreme conditions. For instance, by observing the behavior of gas, stars, and dark matter during a collision, astronomers can infer the properties of these components and test predictions from theoretical models. One particularly fascinating application is the study of dark matter. When galaxies collide, their stars and gas interact differently from their dark matter halos. By analyzing the spatial separation of these components, astronomers can infer the nature of dark matter and its role in shaping the universe. The bullet cluster is a prime example of how galactic collisions reveal the properties of dark matter. This system consists of two colliding galaxy clusters, with the hot gas from each cluster visible in X-rays. Observations show that the dark matter halos, traced by gravitational lensing, have passed through each other with minimal interaction, while the gas clouds have collided and slowed down. This separation provides strong evidence for the existence of dark matter and constrains its interaction cross-section. Studies like this underscore the importance of galactic collisions in advancing our understanding of the universe's most elusive components. As technology advances, simulations of galactic collisions have become increasingly sophisticated, providing detailed insights into their dynamics and outcomes. These simulations use complex algorithms to model the gravitational interactions of stars, gas, and dark matter, as well as the hydrodynamic behavior of gas clouds. By varying parameters such as galaxy mass, velocity, and angle of approach, researchers can explore a wide range of scenarios and compare the results to observations. Simulations have been instrumental in reproducing features such as tidal tails, starburst activity, and the formation of elliptical galaxies, validating our theoretical understanding of these processes. One of the most ambitious simulation projects is the Illustris TNG simulation, which models the evolution of the universe from shortly after the Big Bang to the present day. This project includes detailed treatments of galaxy formation, mergers, and feedback processes, providing a comprehensive view of the role of galactic collisions in cosmic evolution. By analyzing the data from such simulations, researchers can study the frequency and outcomes of galactic interactions across different epochs of the universe, shedding light on how these events have shaped the distribution and properties of galaxies. Galactic collisions are not limited to massive spiral and elliptical galaxies, they also occur among dwarf galaxies, the smaller counterparts that populate the universe in large numbers. Dwarf galaxy collisions are particularly intriguing because their lower masses make them more susceptible to external forces, leading to dramatic transformations. These interactions often result in the stripping of gas and stars, leaving behind irregular or disrupted structures. Studying dwarf galaxy collisions provides valuable insights into the role of interactions in shaping low-mass systems and their contribution to the overall galaxy population. One notable example of a dwarf galaxy collision is the Magellanic Stream, a massive trail of gas that extends from the Large and Small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way. This structure is thought to have formed as a result of interactions between the two galaxies and the Milky Way's gravitational influence. The Magellanic Stream serves as a natural laboratory for studying the dynamics of dwarf galaxy interactions and the processes that fuel the growth of larger galaxies like the Milky Way. As we look deeper into the cosmos, we also observe the remnants of ancient galactic collisions that occurred billions of years ago. These fossil records of interactions are preserved in the structures of galaxies, such as shells, ripples, and streams of stars. By studying these features, astronomers can reconstruct the history of past collisions and gain insights into the assembly of galaxies over cosmic time. The Milky Way itself bears evidence of such events, including streams of stars that trace the remnants of dwarf galaxies that were absorbed into its halo. These streams not only provide clues about the Milky Way's past but also offer a glimpse into the processes that govern galaxy assembly across the universe. Galactic collisions are also key to understanding the life cycle of galaxies. Over time, Galaxies evolve through a series of mergers and interactions, transitioning from one type to another. For example, spiral galaxies like the Milky Way can merge to form elliptical galaxies, which are typically older and contain less gas for star formation. This process, known as hierarchical merging, is a fundamental aspect of cosmic evolution and helps explain the diversity of galaxy types observed in the universe today. By studying galactic collisions at different stages of evolution, astronomers can piece together the story of how galaxies grow, change, and ultimately fade away. On the largest scales, galactic collisions contribute to the formation of galaxy clusters and superclusters, the most massive structures in the universe. These structures are formed through the gradual accumulation of galaxies and dark matter, with collisions playing a central role in their growth. Observing these interactions provides insights into the dynamics of large-scale structure formation and the role of gravity in shaping the universe. For example, the Coma Cluster, a massive galaxy cluster located about 330 million light-years away, contains numerous examples of interacting and merging galaxies. Studying such systems helps astronomers understand the processes that govern the evolution of galaxy clusters and their role in the cosmic web. The future of galactic collision research is bright, with upcoming telescopes and observatories poised to revolutionize our understanding of these events. The Vera C. Rubin Observatory, set to begin operations in the coming years, will conduct a 10-year survey of the sky, capturing the motions and interactions of galaxies in unprecedented detail. The European Space Agency's Euclid mission will map the large-scale structure of the universe, providing new insights into the role of dark matter and dark energy in galactic collisions. These missions, along with advancements in computational power and simulation techniques, will enable astronomers to explore galactic collisions with greater precision and depth than ever before. The study of galactic collisions has not only deepened our understanding of the cosmos but has also reshaped our view of galaxies as dynamic, ever-evolving systems. In earlier eras of astronomy, galaxies were thought to be relatively static entities, existing in isolation. Observations of colliding systems, tidal features, and starbursts have revolutionized this perspective, revealing that interactions are a key driver of galactic evolution. Today, we know that galaxies are intricately connected, influencing each other through gravity, gas exchange, and the transfer of angular momentum. The interplay of gravity during a collision is a fundamental mechanism that dictates the trajectory and ultimate fate of the galaxies involved. When two galaxies approach each other, their mutual gravitational forces create complex tidal fields. These fields distort the galaxies, pulling stars, gas, and dust into new configurations. The tidal forces can also lead to the creation of unique structures, such as bridges of stars connecting the galaxies and vast streams of material trailing behind them. These tidal phenomena serve as visual signatures of galactic interactions and are often used to reconstruct